Quantum entanglement is the phenomenon where the quantum state of each particle in a group cannot be described independently of the state of the others, even when the particles are separated by a large distance. The topic of quantum entanglement is at the heart of the disparity between classical physics and quantum physics. Entanglement is a primary feature of quantum mechanics, not present in classical mechanics.
86.7. Measurements of physical properties such as position, momentum, spin, and polarization performed on entangled particles can, in some cases, be found to be perfectly correlated. For example, if a pair of entangled particles is generated such that their total spin is known to be zero, and one particle is found to have clockwise spin on a first axis, then the spin of the other particle measured on the same axis is found to be anti-clockwise. However, this behavior gives rise to seemingly paradoxical effects. Any measurement of a particle's properties results in an apparent and irreversible wave function collapse of that particle and changes the original quantum state. With entangled particles, such measurements affect the entangled system as a whole. Such phenomena were the subject of a 1933 paper by Albert Einstein, Boris Podolsky, and Nathan Rosen, and several papers by Erwin Schrödinger shortly thereafter. Describing what came to be known as the EPR paradox. Einstein and others considered such behavior impossible, as it violated the local realism view of causality.
Einstein referring to it as spooky action at a distance.
And argue that the accepted formulation of quantum mechanics must therefore be incomplete. The counterintuitive predictions of quantum mechanics were verified in tests where polarization or spin of entangled particles themselves. However, despite the fact that entanglement can produce statistical correlations between events in widely separated places, it cannot be used for faster than light communication. 45v3. Quantum entanglement has been demonstrated experimentally with photons, electrons, top quarks, molecules, and even small diamonds. The use of quantum entanglement in puny events and widely separated traces. It cannot be used for faster than light communication. 45D. Quantum entanglement has been demonstrated experimentally with photons, electrons, top quarks, molecules, and even small diamonds. The use of quantum entanglement in communication and computation is an active area of research and development.